We are now going to motivate a notation for marching through vectors as we compute with elements that are exposed one at a time. Initially, the vectors are partitioned into a top subvector and a bottom subvector. The top subvectors are empty, they contain no components. Next, we expose the first components of the bottom subvectors and multiply them together. Then we append these first components of the bottom subvectors to the top subvectors. Again, we expose the first components of the bottom subvectors, multiply them together, and add them to the partial result that was computed before. Then we append these first components of the bottom subvectors to the top subvectors. This process continues until all components have moved from the bottom subvectors to the top subvectors, at which point the dot product has been computed. We then append the first components of the bottom subvectors to the top subvectors. At this point, the top subvectors contain the components with which we have finished computing, and the bottom subvectors contain the components with which we still need to compute. Looking at a typical place in the computation, notice that the process with which we compute the dot product tracks ranges of components, top subvectors with which computation has already been completed, and bottom subvectors with which computation has yet to be performed. The thick line separates the two. The thin line is used to expose the first component of the bottom subvector. This motivates a very different way of presenting an algorithm for computing the dot product. The algorithm starts by partitioning vectors x and y into top and bottom subvectors. The top subvectors initially have no components, which means that the bottom subvectors equal the entire vectors. The function m returns the length of a vector. As long as the top subvector of x is not the length of the entire vector x, we still have computation to perform. So, we expose the first elements of the bottom subvectors. We do so by repartitioning. The thick line shows that x0 is just a relabeling of x top, while chi1 and x2 denote the first components of the bottom subvector and the rest of the subvector, respectively. The same comments hold for the repartitioning of vector y. The product of the exposed scalars, chi1 and psi1, is added to the result, which is stored in variable alpha. When the top vectors encompass the entire vectors, the loop completes. We now illustrate how the algorithm marches through vectors with our concrete example that computes the dot product of two vectors of length 5. Initially, the top subvectors are empty. In the first iteration, the top components of the bottom subvectors are exposed. The variable alpha is updated. The first components of the bottom subvectors are appended to the top subvectors, and the first iteration completes. In the second iteration, the new top components of the bottom subvectors are exposed. They are multiplied together and added to alpha. The thick line is moved. This process continues until the dot product computation is completed. The bottom line is that we think in terms of regions. We do so when we explain how the dot product can be computed as dot products of subvectors, and we do so when we explain an algorithm for computing the dot product.